Hello dear students, welcome to Pen and Paper Chemistry on YouTube, where we deal with organic, inorganic, physical and general topics in chemistry. These days we are focusing on the properties of aldehydes and ketones, and this is part 5 of the series of videos on properties. What do you have to do? Please get your pen and notebook ready so that we can continue with the lesson. We are now dealing with the oxidation reactions of aldehydes and ketones, that is, what are the products formed and what kind of oxidation reactions are undergone by aldehydes and ketones. So this is a part of the bigger picture, and how does it fit into the bigger picture? As you can see, I have put this part of my flowchart below the nucleophilic addition and nucleophilic substitution. As I had mentioned, we are going to compile it as one big chart for easy reference, right? Oxidation reactions undergone by aldehydes and ketones, and which one of these undergo and which of these are held back. Felling solution, Tollens reagent, Benedict solution, strong oxidizing agents, and finally the Iodoform reaction. All these tests, interestingly, you will be doing in the laboratory as well. They are part of your practical chemistry learning as well. So please pay full attention and make sure that wherever we are writing brick red or reddish brown precipitate, you try to write it with that color pencil or felt pen or sketch pen, so that it embeds in the mind longer. It has a lasting effect and your revision work reduces quite a lot. As always, I'm going to keep the flowchart on the right, as I would expect you all also to do. I hope you've drawn the flowchart before you continue playing the video, so that we can refer to it and write the reactions. Oxidation reactions of aldehydes and ketones are very, very specific. If you notice, in the case of aldehydes, we've got the CHO group, where this CH is easily oxidizable. So this CH converts to COH even in the presence of mild oxidizing agents like Tollens reagent, Felling solution, Benedict solution. Whereas in the case of ketones, now here I've put an alkyl group, the other I've taken the example of CH3. There is no oxidizable CH group. With the result, we find that with mild oxidizing agents, our ketones do not react. What about strong oxidizing agents? As I said, ketones do not react in the presence of strong oxidizing agents. Now, can you recall some of the strong oxidizing agents that you've done? Yes, we have listed them in the chart as well. So, strong oxidizing agents, concentrated HNO3, acidified potassium permanganate. Remember, the purple color gets decolorized. Acidified potassium dichromate from orange to green. We've done these. We've talked about, yes, perfect. We've talked about these in alcohols as well, because we talked about the conversion of alcohols to aldehydes to carboxylic acids, right, in the presence of these oxidizing agents. What about reduction? Acids are reduced to aldehydes and aldehydes are reduced to alcohols, the reverse. So in the presence of strong oxidizing agents, what will happen is, yes, aldehydes do get oxidized and they get converted into the carboxylic acid. On the other hand, the ketones, they undergo what we call as oxidative cleavage. Oxidation, but with breakdown. When I say Tollens reagent, what comes to mind is the silver mirror test. As simple as that. Why? Because when you do this test, this is the kind of observation you are going to make in the laboratory. This image I have picked from Wikipedia. So You can see here. In fact, you will be doing this test in the laboratory also now to understand the details of this process. What is Tollens reagent? You take a solution of silver nitrate, because what is there is Tollens reagent is actually freshly prepared in the laboratory. They won't keep it for long because it gets oxidized. So what will happen is silver nitrate, freshly prepared silver nitrate solution, we add a few drops of an alkali, usually sodium hydroxide or ammonium hydroxide, few drops. Now when we add a few drops, this gets converted into silver oxide, a black precipitate. Now what we do is, next step is we continue to add the ammonium hydroxide in excess till the precipitate dissolves. Now why does the precipitate dissolve? It dissolves because of the formation of this complex, diamino silver complex. Remember coordination compounds which we've already covered on the channel? Yes, so diamine silver complexes form. It's still in an alkaline medium. So what will happen? The aldehyde will combine with this complex in an alkaline medium, aldehyde or the ketone. So we'll try with both the samples. I have written the reaction with an aldehyde, a general equation. The aldehyde, as we said, gets oxidized. So this converts to OH. So if you see here, we'll get RCOOH, which is an acid, a carboxylic acid. Ammonia, water and the silver mirror is observed. Now this silver mirror is what helps us to identify aldehydes. Why aldehydes? Because ketones do not give this test. There are exceptions to this because we find that there is a set of ketones what we call as the alpha hydroxy ketones, which yes do undergo the silver mirror test. Aromatic aldehydes, yes. So aliphatic aldehydes, aromatic aldehydes, alpha hydroxy ketones and formic acid as well. Formic acid, why will formic acid undergo this reaction? Look at the structure once again. You see it's got an easily oxidizable CHO group. So C double bond O, OH, OH. What does this become? What compound is this? Think. I like to quiz. Many students are not able to crack this. They say this is diol. Did you think this is diol? How many of you think this is diol and a ketone? Okay, look at this. It's H2CO3. Oh yes, ma'am. This didn't come to our mind, right? And carbonic acid is a weak acid. So what happens is when you treat formic acid with Tollens reagent, what we will get is our final product will be carbon dioxide and water. The product of oxidation of formic acid would be CO2 and water. Although we will again cover this under the topic of carboxylic acids. But for now, it's an interesting piece of information which you can note down. To make things simple for you and to enable you to write down the notes and have it all compiled, I've given you the Tollens reagent. What is Tollens reagent? An ammonical solution of silver nitrate. So you add a few drops of NaOH or ammonium hydroxide to form a black precipitate of silver oxide. Add ammonium hydroxide in excess till the black PPT dissolves. Now observe one more thing. Here in this picture, two test tubes are shown. The first test tube shows the silver mirror test which you get with an aldehyde. The second would be with any compound which does not give you the silver mirror test. So that could be any alcohol, halo derivative. It could be a ketone as well. I'm not going into the details of the silver mirror test with the other compounds. Aromatic aldehydes, again, we will be taking up separately in continuity of the aldehydes and ketones chapter here, right? So this is a piece of information which should help you to understand the topic better. Have you written the equations? Please write the equations. Please make sure that you check the balancing. I have not balanced this. Please balance the equation. Next is the reaction with Fehling solution or Benedict solution. This gives a brick red precipitate or a reddish brown precipitate on treatment with aldehydes, and interestingly only aliphatic aldehydes give the reaction. So let's first understand what is Fehling solution. Now you must be wondering Benedict solution. In some of the syllabi, Benedict solution is not mentioned, but it's not so difficult because it's basically both of them are nothing but solutions of Cu2 positive ions in an alkaline medium. How do we prepare Fehling solution? Fehling solution is actually Fehling's A and Fehling's B. What is Fehling's A? It's nothing but an aqueous solution of hydrated copper sulfate, CuSO4.5H2O. The second solution is nothing but an alkaline solution, that means made alkaline with sodium hydroxide of sodium potassium tartrate, which is also known as the Rochelle salt. This gives us Fehling solution. Now when I say Benedict solution, my solution A still remains the same. Instead of sodium potassium tartrate, I am taking sodium citrate here. That gives me Benedict solution. So sodium carbonate, sodium citrate and hydrated copper sulfate solution again gives me copper ions in an alkaline solution. So basically both of them are same. Now you know that copper ions have a blue color. That is why you would have noticed that in these slides I have written them in blue so that it's easier for you to remember. But the brick red precipitate I have written in red again so that it's easier for you to remember. Look at the picture here. This makes the things clear. So what you have here is when you just take the aqueous solution, initial Fehling's A and Fehling's B, you get a bluish color, right? A blue colored solution. Now when you add the aldehyde and slightly warm it, what you get is a brick red, orange or green or yellowish PPT depending on what type of aldehyde it is, because we do use these compounds, that is Fehling solution and Benedict solution, to determine the concentration of sugar, the amount of sugar in the urine. So reducing sugars do give this test, and that is why I used the term that you could have different colors of the precipitate depending on the concentration of the reducing sugar. But for the level that I am teaching right now, we are concentrating on grade 12. I think for you brick red precipitate should be a good definition or should be a good benchmark to decide whether a particular compound is an aldehyde or not. Look at the reaction. Again, what will happen? Oxidation. So RCH double bond O. Mild oxidizing agent. This gets oxidized OH. So you again get RCOOH. Now copper Cu2 positive gets reduced to Cu positive. You look at the product which is formed, Cu2O. That is copper 1 oxide. So the oxidation state of copper has changed from 2 to 1. I hope your fundamentals regarding oxidation and reduction are in place. If not, then there are videos on the channel explaining oxidation and reduction and how to balance ionic equations in a very easy way. Very, very easy way. You'll practice with me and you'll enjoy the topic much more. So make sure if your fundamentals are not in place, you do revise that. Right? For Benedict solution, reaction with Benedict solution, the reaction again is exactly the same. So you actually don't need to worry much about Benedict solution. Only thing is, instead of the tartrate ions in the solution, that is a combination of citrate ions. That's all. The complex is with citrate ions. Now, do aliphatic aldehydes give this test? Yes, they do. Do aromatic aldehydes give this test? No, they don't do. So benzaldehyde actually does not give this test. C6H5CHO? No, it doesn't give. Do ketones give this test? No, they don't. So let me strike them off. Do alpha hydroxyketones give this test? Yes, they do, because they can be tautomerized to give you the aldehyde. Does formic acid give this test? Yes, it does. Right? Now, if you recall, in the case of Tollens reagent, we had said that aliphatic aldehydes, aromatic aldehydes, alpha hydroxyketones, formic acid, they give. So, aromatic aldehydes can be oxidized by Tollens reagent, but cannot be oxidized by Fehling solution. So, which one of the two do you think is stronger as an oxidizing agent? Fehling's or Tollens? Yes, of course, Tollens reagent is a stronger, although both of them are in the category of mild oxidizing agents, but even in that, your Tollens reagent is stronger as compared to Fehling's or Benedict solution. That you can very easily make out from looking at the ions in the activity series, right? So if you see in the activity series, copper is higher in the activity series compared to silver. Correct? Coming to reaction with strong oxidizing agents, we've already listed the strong oxidizing agents. Do I need to repeat? Yes. Okay, so we'll have acidified potassium permanganate, acidified potassium dichromate, concentrated HNO3. Here, as I mentioned earlier, yes, aldehydes undergo oxidation to give you carboxylic acids. Now, what you have to do is you have to complete these equations for me. I've written 1, 2, 3. So, write down all the 3 oxidizing agents, write the product. Acid. What acid will be formed? You can check your answers. I will be posting the same notes, the teacher's notes on the site, Pen and Paper Chemistry. It's a Google site. You can see I'm posting the link in all the flowcharts as well. Right? Okay. Now coming to the ketones. In the case of ketones, what we mentioned was, yes, there is oxidation, but there is breaking down as well. Where will it break down from? Right, that's the big question. It can break down from here. When it breaks down and undergoes oxidation, what will we get? So, CH3 part breaks down, so we may get HCOOH plus, now start from here, CH3, CH2, COOH. These are all the possible products we are writing. Or it could break down from here. So, first was the A option, then is the B option. Would you like to try and write the products of oxidation in, option B? Go ahead. So we could have, yes, CH COOH, right? It's this group which gets oxidized. Remember, we are using strong oxidizing agents. And then CH3COOH. If you notice, our products have lesser number of carbon atoms compared to the original. Our original ketone was 1, 2, 3, 4. Okay, what have we got here? Did I get the products right? No, this A1 should be CH3CH2COH. Wait. Let me correct myself here, right? So CH3CH2COOH. Whereas when it is breaking down at B, then it will be CH3COOH and CH3COH. So breaking down can take place at different points. Next and very important reaction, iodoform reaction, but you notice the screen has turned blue. Why do you think it has turned blue? I have just imported this from the lecture on alcohols, where we have dealt with the iodoform reaction in a lot of detail, where we explain, just to give you in short, any compound containing CH3CO group or CH3CHOH group which can be oxidized in the presence of an alkali will give us a pale yellow crystalline precipitate of iodoform, which has a penetrating sweetish smell like the smell we feel in hospitals, because it's used as a disinfectant and antiseptic as well. So only these compounds, CH3CO and CH3CHOH, right? So that's where I think our ketones have an upper hand, correct? Not necessarily, because there are certain aldehydes as well which give this test. So look at it again. CH3CO, CH3. Yes, there is this CH3CO group. CH3CHO. CHO. Will it give this test? Yes. Look at the structure, CH3CO group, right? We didn't say that it should not have any other group attached to it. It has this CH3CO group. Look at C2H5CHO. CH3, CH2, C. Okay, it does have CO, but it's got CH2CO group, right? So will it give this test? No. CH3CO, CH2, CH3. Go ahead, try them. What about ethanol? Does it give this test? Yes. Again, I had explained to you with the help of this expanded structure, we know that this gets oxidized to the CH3CO group. So that is why CH3CHOH group, right? You can see very clearly. That's what we mentioned, CH3CHOH group. So will it show iodoform reaction? Yes. Why am I explaining it again? This is a test that you will do in the laboratory. But sadly, in a video, I cannot share the smell. So I cannot insert a smell just like I had inserted the pictures for the Tollens reagent test and the and the Felling solution test, right? So next time you go to the laboratory to do this test, make sure that your eyes and ears and nose, everything is open for the observations. These are some of the examples that we had taken, and this is how we had defined the haloform reaction or the iodoform reaction, sharing the same slide. So what is the product? So what we've got here is the ketone reacts with iodine in the presence of an alkali to give us CHI3. It gets oxidized to give us a yellow precipitate of iodoform, right? Question was, why don't we do this test with chlorine? Because the product over here would be chloroform, and we definitely don't want to be smelling chloroform in the laboratory. Do we want to? Right? So these products are colorless. That is why we are doing it with iodine. Yes, the reaction does take place with chlorine and bromine, but practically it is done with iodine, hence the specific name iodoform reaction. Right? Does that make things easy? And there are blanks to be filled by you. I hope that this chart is now making sense, and we've got our nucleophilic addition followed by elimination, reduction and oxidation reactions in place. Is the topic over, teacher? It's been a long topic. We are doing 2 topics simultaneously, so why do you want it to end so soon? I'm going to come back with some very unique reactions of aldehydes and ketones. So we are yet to do the aldol condensation, Canizaro's reaction, and maybe a mention of polymers. So do stay tuned, stay connected, and request you to share. I am not advertising on this channel just to keep the data low. So just to request you, please share this gift of knowledge with friends and classmates so that they can also enjoy this learning. See you in the next video. Stay healthy, stay happy.